Hello students, today I am going to discuss about electric flux. We already studied electric field lines and torque. Now what is meant by electric flux? It means the total number of electric lines of force that normally passes through a surface. Just look at the figure that I am showing you here. Here you can see the green lines. Those are the electric field lines. So total number of electric field lines passing normally meaning perpendicular, normally through any surface is called electric flux. The surface can have any irregular shape. Out of that irregular shape, just imagine you are taking any small portion of that surface and mark that as ds. S means the surface area of the given surface. When I say ds, it is the small portion of that entire area, small portion of the entire area. So you take anywhere a small portion which is ds, and along that surface you have to draw a normal meaning perpendicular. That normal is called area vector. So area vector is a perpendicular line which is drawn normal to any surface. You can see in the figure some yellow lines. Those are the area vectors. So I have drawn 5 yellow lines. Out of that you take any line. See, for example, take a line ds which makes an angle theta with the electric field. Theta is not 90 degree, any arbitrary angle theta. Then electric flux passing through that small surface is given by d phi. Phi for electric flux. D phi means flux for a small surface. So d phi is equal to vector E dot vector ds. And we have already studied A dot B is AB cos theta. So here vector E dot vector ds is EDS cos theta. Now how will I find the total electric flux passing through the surface? Total electric flux can be given as surface integral vector E dot vector ds, which is ES cos theta, or I will write vector E dot vector S. Since it is a dot product, electric flux is a scalar quantity, and SI unit of electric field is Newton meter square Coulomb raised to -1 or Joule meter Coulomb raised to -1. Now, if the electric field and area vector are in the same direction, you can say flux is positive. And if electric field and area vector are in the opposite direction, you can say flux is negative. Next topic is Gauss theorem. Gauss theorem tells that the surface integral of electric field intensity over any closed surface in free space is equal to 1 by epsilon 0 times the net charge enclosed within the surface. Just now we have studied how to calculate the flux. Flux can be calculated by phi is equal to surface integral vector E dot vector ds, and that can be given as 1 by epsilon 0 times the total charge. Total charge is written as sigma qi. So in short, we can write phi is equal to q by epsilon 0. That is the simplest form of representation. Phi is equal to q by epsilon 0. Now let us see how to prove that. Imagine a charge q is placed at the center of the sphere. The radius of sphere is r, and take a small surface which is ds. Now, for a point charge, electric field is directed outward, so electric field is marked by the blue arrow, and area vector, as I told, area vector is drawn by drawing a normal with the surface we are selecting. So we choose a small surface on the sphere, draw a perpendicular line, that is given as the yellow arrow. So both the vectors, that is electric field and ds, both of them are in the same direction. So theta equal to 0 and cos 0 is 1. So look at the derivation now. D phi is equal to vector E dot vector ds. Electric field equation is 1 by 4 pi epsilon 0 q by r square into r cap dot ds into n cap. So I write d phi is equal to 1 by 4 pi epsilon 0 q into ds by r square r cap dot n cap. So both of them are unit vectors, and as I told, vector E and vector ds are in the same direction. Theta is 0 and cos 0 is 1. So that dot product of unit vector become 1. Therefore the answer becomes d phi is equal to 1 by 4 pi epsilon 0 q into ds by r square. Now, how will you find the total electric flux? Total electric flux means flux through the entire sphere. You can do integration. So integral d phi. That is integral 1 by 4 pi epsilon 0 q by r square into ds. Since q by 4 pi r square epsilon 0 is constant, I can take it outside the integral and only integrate integral ds. ds is a small part of the sphere. So integral ds means entire surface area. So 1 by 4 pi epsilon 0 q by r square into integral ds is entire surface area, which is 4 pi r square. So you can see 4 pi r square and 4 pi r square cancel. The remaining thing is q by epsilon 0. Therefore, we can conclude phi equal to q by epsilon 0. That is the Gauss theorem. Now, let us see how to find the electric field intensity due to an infinitely long straight wire of linear charge density lambda using Gauss theorem. Look at the figure. The orange color line is actually a conductor which is infinitely long, and conductor is charged positively. We have to find electric field intensity due to this conductor. So what I am doing is to apply, in order to apply the Gauss theorem, we have to imagine a surface which is called Gaussian surface. Gaussian surface is an imaginary surface which we use to apply the Gauss theorem to find the electric field intensity. Gaussian surface can have any shape. It can be a sphere, it can be a cylinder, it can be a cuboid, or any irregular shape. But for our convenience, if the charge is a point charge, we will use sphere as the Gaussian surface, and if it is a line charge, linear charge, then we will use cylinder as the Gaussian surface, and if it is a thin sheet of charge, we will use cuboid or cylinder as the Gaussian surface. So here we are taking line charge, so we use cylinder as the Gaussian surface which passes through the conductor. Now cylinder has three parts. The first one is marked as A, which is the circle, and the second also will be a circle on the left side, which is marked as B, and the third one is marked as C, which is the curved surface area of the cylinder. Now look at the point A. At the point A, you can see that electric field and area vector both are perpendicular to each other. Theta is 90 degree. Similarly, at point B, electric field and area vector are perpendicular to each other. There also theta is 90 degree. So why I marked electric field in the downward direction? Because due to a positive charge, electric field is normally downward and upward. So here I marked downward. And at the point C, you can see that electric field I marked as perpendicularly upward. Now, at the point A and B, theta is 90 degree, and at the point C, area vector and electric field are in the same direction, so theta is 0. So we are going to apply Gauss theorem. Phi is equal to surface integral E dot ds, which is q by epsilon 0, and the surface integral E dot ds is split into three parts. Integral E dot ds along the surface A, integral E dot ds along the surface B, and integral E dot ds along the surface C. As we discussed in the figure, along the surface A and B, theta is 90 degree, so cos 90 will be 0, and at the surface C, theta is 0 degree, so cos 0 is 1. So I have written like this: integral E dot ds cos 90 plus integral E ds cos 90 plus integral E ds cos 0. The first two terms, the answer will be 0 as cos 90 is 0, and only the third term prevails. Therefore, the answer will be E into integral ds. Cos 0 is 1, so E into integral ds. Therefore, we got only the curved surface area of the cylinder. And integral ds means curved surface area, which is 2 pi RL. Therefore, the equation is surface integral E dot ds equal to E into 2 pi RL. Now, q by epsilon 0. We studied linear charge density lambda equal to q by L. Therefore, q can be given as lambda into L. That is what you are seeing here. So instead of q by epsilon 0, I wrote lambda L by epsilon 0. So put this equation in the first equation. So instead of q by epsilon 0, I can write lambda L by epsilon 0, and instead of integral E dot ds, I can write E into 2 pi RL. So substituting both of them, I will get E into 2 pi RL equal to lambda L by epsilon 0. From there, E can be found as lambda by 2 pi epsilon 0 R. Okay. So the electric field intensity due to an infinitely long conductor is given by the equation E is equal to lambda by 2 pi epsilon 0 R. The direction of electric field intensity is radially outward from the positive line charge, and for a negative line charge it will be radially inward. Now please note one more thing that I have written here. The electric field intensity is independent of the size of the Gaussian surface. It depends only on the distance of point of consideration. That means the Gaussian surface should contain the point of consideration. What I mean is, according to the equation we got, phi is equal to q by epsilon 0. Phi depends only on q, does not depend on the radius of the Gaussian surface or size of the Gaussian surface. So we only have to consider the charge enclosed by the Gaussian surface to find the electric field intensity. Okay, thank you.